So this next video is on graphing cosecant, secant, and cotangent. So to graph these, I'm going to start with their reciprocals, use the attributes of their reciprocals in order to sketch the graph of these reciprocals, which I would suggest doing going forward, because once you see that relationship, it makes it a lot easier to remember what this is going to look like and what the graph will do. So I'm going to start with a sketch of, we're doing cosecant, which means I'm going to start with a sketch of sine. So we'll still use the same intervals. So we have negative pi over 2, and then we'll have pi over 2, actually fix that, pi over 2, and then just so it's equidistant, we'll have pi. Still have positive 1 and negative 1. So even the same benchmarks as sine, we're going from negative pi to pi and then from negative 1 to positive 1. So sine is odd, so we can show that it has that rotational symmetry. And instead of drawing a solid line, I'm going to draw a dashed line because we're using sine to sketch cosecant, but it's not the focus. It's not the actual graph that we want to see. And then I need to fix this right here. Boom, and then it needs to align with that maximum. Then that should be positive pi over 2. Okay, so cosecant, we'll go ahead and start writing this down. Cosecant has the same, almost the same attributes as sine. Now, the sketch is obviously going to look different, but when I say attributes, I mean that the period is also 2 pi. And because sine is odd, that means its reciprocal will also be odd. It's an odd function. So we'll see that rotational symmetry. And it's also an oscillating function. So remember, oscillating is just going to mean repeating. It's not the same type of smooth oscillation as the sine curve, but it still repeats. And then a quick note, we talked about this when we were evaluating in the last video. When sine theta is equal to 0, when we take that reciprocal, we get cosecant theta. That is equal to 1 over 0, which means undefined. Therefore, we will see a vertical asymptote. So let's start with that. So in our sketch, we have 3 points within one period for sine that cross the x-axis or have an output of 0, which means for its reciprocal, when we flip that, it's going to be undefined, so we will see vertical asymptotes at those points. So those 3 points will be at negative pi. It's passing the horizontal axis there. It's also passing at 0. And it's also passing at pi. So the points I'm referring to are here. These x-intercepts that are on sine, they are going to be vertical asymptotes for its reciprocal. All right, the next thing I want to talk about is, let's look at pi over 2, because we need to figure out what are going to be the other parts of this curve. So if we look at pi over 2, let's solve for sine of pi over 2. Well, based on the sketch and the unit circle, sine of pi over 2 is going to be 1. So now let's solve for cosecant of pi over 2, which is going to be 1 over sine of pi over 2, which equals 1 over 1, which is going to result in the same output 1. So that means cosecant and sine are going to share an output at pi over 2. So that means the input and the output are going to be the same. So these are going to be the same point on both graphs. Now, because sine is odd, cosecant is odd, which means the same can be said for this point over here because of that rotational symmetry. So I don't even have to do the math for that. Based on the attributes of an odd function, I can go ahead and plug that point in there. So now let's think about this. If we think of let's do this. Where can I put this? Let's think of y equals x. Well, y equals x is a function that is always increasing. Well, you should read it left to right, always increasing. Now take its reciprocal, y equals 1 over x. This one's a little bit more, well, it's obviously more complex because once we get into rationals, we now have a vertical and a horizontal asymptote. But this function, even though there's a break, if you look at it, it is always decreasing. And that's because it's the reciprocal of a function that is always increasing, okay? And it still has that rotational symmetry as well. This same attribute can be applied to trig expressions. So if we look at this, sine is decreasing into that point, which means cosecant should be increasing into that point. So I can draw something like this. And then as I go forward, sine is increasing here, which means cosecant will decrease. And it decreases to infinity. And then even though there's an asymptote there, sine is increasing into pi over 2, which means cosecant will decrease and then increase. So we can see that reflection from those minimums and maximums that are occurring. And this happens repeatedly. So if we were to sketch this for another period, we would see another curve here and here along with a vertical asymptote in between them. So it would go on for infinity. But this is how we use sine to sketch cosecant, all right? Now, if you just remember that it's an odd function, you'll be able to remember that that vertical asymptote is on the y-axis, and then you can use the minimums and maximums from sine for that. So next unit, just like the first three, we will be doing transformations. So we'll go ahead and get the table in for that. Now, luckily, you can just use the table from sine. So for sine, we had negative pi over 2, 0, pi over 2, and then pi. Now, instead of the zeros that we had for sine, you're going to replace those with vertical asymptotes. And then we also just prove that these are equivalent, so it will share those outputs. So -1 and +1. So that will be your transformation table for next unit. And one thing I want to talk about is its domain. The domain is broken up by these vertical asymptotes, where the one that's closest to 0 falls on 0. So this has a domain restriction of x cannot equal 0 plus pi k, because it occurs every pi, just like tangent. But we just write it simply as x cannot equal pi k. And just recall that k represents an integer. This way we we exclude all of the vertical asymptotes from our domain. The range is going to be -infinity to -1 union +1 to infinity. So that first part, the -infinity to -1, includes all of the curves here because they go to -infinity. The next part, 1 to infinity, includes all of these curves because they go up to +infinity. So the range is all real numbers except values that are from -1 to +1, but this is how we write it in interval notation. The next one is secant. It says 2 periods. I'm only going to graph 1, but we're going to do the same thing we did for sine, but for cosecant, but instead of using sine, we will now use cosine. So we'll sketch another vertical axis and horizontal axis. But for the horizontal axis, you'll want to include it a little bit further. I'm trying to debate whether I want to do it how I did it in class. Yeah, we'll do how we did in class because that's mainly who's watching this. All right, so for cosine, we have -pi, -pi over 2, pi over 2, and pi. And then again, +1 and -1. Go ahead and include 3 pi over 2. All right, for cosine, now we start at -1, pass through the horizontal axis at -pi over 2, come up to +1, pi over 2, and then back down to -1. So this is the period that we sketched in the notes for cosine, okay? All right, so a couple notes. I think that's all I had for the first one. Yeah, so a couple notes. This has the, whoops, switch back to the color. This has the same attributes. Handwriting's terrible. Same attributes as cosine, such that the period is 2 pi. It's well, cosine was even because it has that vertical symmetry about the y-axis. Therefore, secant is also an even function. And it's also oscillating. And then again, let's make another note. If we make a note when cosine theta is equal to 0, which is technically 0 over 1, that means secant theta is equal to 1 over 0, which means therefore there will be vertical asymptotes. So this is not specific to just sine and cosecant. This is true for all of the reciprocals, all trig reciprocals. All right, so let's start with the vertical asymptotes. If we look at this, instead of starting with a vertical asymptote, we see that the vertical asymptote is at -pi over 2. So we'll go ahead and sketch one there. And then the next vertical asymptote is at pi over 2. So what is similar is that same for tangent and same for cosecant, these vertical asymptotes are occurring every pi, right? So think of this as -1/2. This is 1/2. If you get the total distance, we take we'll add the -1/2. We end up with, whoops, we should be subtracting that. So 1 minus -1/2, we end up with 1. So that's 1 pi. So when we construct our domain restriction, we'll also use that pi distance as well. Okay, so now the relationship that we saw with the mins and maxes in cosecant and sine, they are going to be the same for cosine, okay? So wherever you see a minimum, you can go ahead and put a dot, same with the maximum. And then that increasing-decreasing relationship, that's also going to be the same. So cosine is increasing here, which means secant will be decreasing. And then in the middle, we'll go from decreasing to increasing because cosine is increasing to decreasing. And then over here, we will just decrease. Okay, so when I first started teaching pre-calculus, we used to just write it like this, okay? But as we went forward, we noticed that students were more comfortable with starting at an asymptote instead of drawing these broken curves. Now, for me, you can do either one, as long as you show, okay, is it 1 period, is it 2 periods, or sometimes we will provide a domain restriction, like starting at -pi over 2, so you'll have to follow them, okay? As long as you show a full period, it doesn't matter to me. But the second way that I've shown it is we've shifted and added 1/2 pi. That way we get to another vertical asymptote. And it also completes this curve over here. That looks weird. Completes this curve over here, okay? So, which means we would ignore this over here. So that way you would have a complete period with 3 vertical asymptotes and 2 complete curves. So again, choose whichever one's easier for you. Sometimes people choose the first method because it makes creating the table a little bit easier. So the table, I'm going to use the second method for with the 3 vertical asymptotes and the complete curves, okay? So I'm going to start at -pi over 2, 0, pi over 2, pi, and 3 pi over 2. But if you want to start at -pi, that's okay. Just know when you transform in the next unit, you're going to have broken curves, which that's fine if it's easier for you. All right, at -pi over 2, we have a vertical asymptote. And at 3 pi over 2, a vertical asymptote, pi over 2 vertical asymptote. This is another reason it aligns better with cosecant when you do this because we start and end with vertical asymptotes. And then secant is just flipped from cosecant, so we have +1 and -1. All right, the domain is going to be, we can see that there's a vertical asymptote at -π/2 and π/2, 3π/2. So this has the same domain restriction as tangent. So x cannot equal π/2 plus pi k. And then the range will be the same as cosecant, -∞ to +1, sorry, -∞ to -1, union 1 to infinity. The last one we're going to look at is cotangent. So again, same process. We're going to start with the sketch and then include a little bit more to the right. The same thing is going to happen for cotangent that happened with secant. We want to try and keep the curves connected, but again, if the other way is easier for you, then continue to do that method. So for tangent, we started at -π/2. And then +π/2. Sorry, let me expand that because we also had the 4's in there. So -π/2 and -π/4. And then 0, π/4, and then π/2. Now for this one, go ahead and include 3π/4. And pi. So I'm going to do tangent in all white, including its vertical asymptote. So tangent has a vertical asymptote at -π/2 and +π/2. And then it went through -π/4 at -1. I forgot my vertical ticks. And then it went through the origin and then at +1. So I'm going to go ahead and tick that in as well. Okay, that way there's not too much happening. So same thing, it has the same attributes. Cotangent has the same attributes as tangent. Meaning the period is pi, just 1 pi. Tangent is odd, therefore cotangent is also odd. It'll have that rotational symmetry about the origin. And then it repeats, so it's also an oscillating function. And similar to secant and cosecant, whenever tangent is 0, cotangent will have a vertical asymptote. So because tangent crosses the origin, cotangent will have a vertical asymptote here. All right, so also because tangent has a vertical asymptote here and it has one here, that means cotangent will pass through the x-axis there. So now for the first time, we're using the opposite relationship. All right, so that means tangent is always increasing. It's monotonic, which means cotangent will always decrease. And it's also going to pass through these points on tangent, right? So it's going to pass through here, and it's going to pass through here, okay? So we have 2 points here. It's always decreasing, and then it's also going to go through here. So if you want, you can use this as your sketch, as your pi sketch. But again, both of the curves are disconnected. We have one asymptote in the middle. We typically like to begin and end with a vertical asymptote so that we can see the full curve. So what we did was, if I look at this and I follow the periodic pattern, I have a vertical asymptote at 0, which means I will have another one at pi, because the period for cotangent is pi. And then I can also see that this is decreasing. It's going to decrease through 3π/4 and -1. So it's going to continue to go in that direction. Let me fix my curve here, just so I can connect them all. So it's going to look something like this. and then our vertical asymptote here. So this is what we typically teach now. We ignore this side. That way we see one curve and two vertical asymptotes for cotangent. So we also mimic the table for this. So we start at 0, and then we go to pi over 4, and then pi over 2, 3 pi over 4, and pi. So keeping it sandwiched in between those two vertical asymptotes, I start with a vertical asymptote, end with a vertical asymptote, and instead of going from -1, 0, 1, it's now always decreasing, so we start at 1, 0, -1. And this is what we will use for the transformation table in the next unit. The domain for this is it's going to be the same as cosecant because we have that vertical asymptote on the vertical axis. So it's going to be x cannot equal pi k. And then the range is going to be all real numbers, or you can say -infinity to infinity. You can say either one, but you have to recognize both. All right, that completes this unit. I hope this video was helpful.